It's entitled Superball. And in this lab, you're going to be working on two programs. One's entitled SB Analyze, and the other one is SB Play. The main goal of this lab is to write a game player for the Superball game. So the two programs you'll have to hand in to submit is the SB Analyze and the SB Play, the two files you create. Also every year, some people ask for the source code to SB Player, but he's unable to give it out because if he did give out the code, it'd be too easy to make a game player for the lab. But he does provide two binary players to run the game. One is SB Player for the Unix machines, and he also has an SB Player Mac that is compiled for Macintosh. Also, there is an additional multi-platform player that you can use that's a jar file, and it should be able to run on any operating system. For this lab, you're going to be writing the analyze and the solve the game player using the disjoint sets. And for this lab, you should use the disjoint set library provided in the lecture notes. And so you should include the dj.h into your programs, and it should work with any of the implementations from the lecture notes. So you can choose which implementation you want to use and go with it. So Superball is a game that was part of the Windows CD for Windows 95, and it works as follows. You have a grid that's 8 by 10, which makes up the game board for Superball, and each cell of the board can be empty or it can hold a color. And each color has a corresponding point value associated with it. So purple cells are 2 points, blue cells are 3 points, yellow is 4, red is 5, and green is 6 points. When you play the game and open up the game, it starts out with 5 random colors on the board, and then each turn you can perform one of 2 actions. The first action is to swap 2 colored cells. And then after you do a swap, 5 new random cells will be added to the grid. The other action you can perform is a score. And to score a cell, the cell must be in one of the goal cells. So you can choose one of those goal cells and score it. The goal cells are in rows 2 to 5 and columns 0, 1, 8, and 9. Everything is 0 indexed on the grid. In order to score a color, you have to have at least 5 colored cells touching the cell that's in the goal. If you have 5 or more colored cells attached to it, you can select it, score it, and your score will be the sum of the value of each of the colored cells that gets cleared off the board. Once you do a scoring action, 3 new cells are added to the board at the end of that. So the player that Dr. Plank wrote is a Tickle TK shell scripted Superball player. It's located in Dr. Plank's home directory. So in order to play it, you should copy the Superball directory to your home directory using the copy command, and then you can play it using the executable that you've copied over. So when you fire it up, this is what you'll see. This is the game player. You're given the grid, and it's already filled in with 5 of the colors. So when you play it, you can click on 2 different colors, and you'll have those colors swap. In this view, the asterisk cells are the goal cells. So you can start swapping, and as you swap, 5 more cells will be added each time. So you're trying to group up clumps of colors, like this green section, so that you can then score that section. So in this case, he's going to collect them by clicking any of the goal cells in the green block, and then clicking the collect button. That will clear those cells off of the board, calculate the point value, and give him the corresponding score for that collection. And then again, he keeps playing and he keeps doing swaps until the board fills up. Once the board fills up and you have no valid collect that you can do, you have to just swap 2 cells, and then the game will end because there's no place to put new cells on the board. So again, he's at this point, he can't do anything, so he swaps 2 cells, and then he gets the game over since the game's now over. So one of the goals to playing this game is to swap the colors in the clumps, clear the clumps out, and keep from filling up the game board, because that's the in-game condition. So I'm going to show you how to launch it. I've already copied over his Superball file into my home directory, so I can run it. Using the Superball, that'll open up the game. So then now once the game is open, you can play the game by clicking on two colors, and that'll cause it to swap. As you do that, more colors will keep being added on to the board. And eventually, you'll get to the point where you'll have a group of 5 in the goal cell, so that then you can clear out those cells and gain some points. So the first thing you should do when getting started is go ahead and copy over the Superball program and start playing with it to try to come up with strategies on how to best solve the game. So that's the GUI version. It's probably the best for playing with on your own. But for the lab, to make it easier for your program to play the game, there's a text-based ASCII art version of the game that your program will be using. So for the text-based version, you have the following parameters passed into it. You can choose how many rows the game board will have. You can specify the number of columns for the game board. And then you can also set the minimum size that you need to be able to score. So for the GUI version, the number of rows is fixed at 8, and the min score size is 5, which means you need a group of 5 to be able to score. The colors is a string that represents the colors. So, and then the first color is worth 2 points, and every color after is 1 more point. So in order for it to match the GUI version, the parameters should be P, B, Y, or G, which gives the point value of purple 2, blue 3, yellow 4, and so on for the point values. So in order to play the ASCII version of the game interactively, you can call it like this, with the interactive and output mode to yes, and not specifying a seed or a player. Then it will bring up your ASCII grid that represents the grid of the colors, and it'll prompt you for a move. You can input moves using these 2 commands. You have a swap move where you give it the row and column of 2 different cells. And you also have a score command where you give it the row column of one of the goal cells that are eligible to being cleared. So when you're playing it initially, you're presented with this. You don't have any scoring you can do, so you have to do a swap. Once you do a swap, it will add more cells. And so now Dr. Plank does an example of playing the ASCII art game. So you do a swap, 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 keep swapping until you build up a group of cells you can collect. Once you have a group of cells you can collect, you can do the score command, and that will clear out, that will collect the scores, or the cells, and now your score will be a positive value because it collected those cells. And then, so you'll note in his example, he could have collected the cell in the previous step, but he wanted to make the patch bigger, so he did one more swap before collecting to have a bit larger patch to collect. So the first program in the lab directory is written for you. It's the SB read. And what it does is it just reads in a game board and does some basic analysis of it. So the parameters are the same, and then you give it an ASCII board. So this board can be represented with this ASCII representation of it. And then when you run SB read on it, it'll give you the empty cells, the non-empty cells, the number of pieces in the goal cells, and the sum of the values of the pieces in the goal cells. So in this case, there are 3 purple cells, 1 yellow, 3 green, and 1 red. And that's how the total value is calculated. So you should take a look at SB read because it has a Superball class, which represents reading in the Superball grid. So you have a constructor, the RC, MSS, and empty values, where MSS is that min score size you need to be able to collect. Empty is the number of empty cells on the board. board is a vector of r times c integers, where element ij is the entry board I times c plus j, and it is either going to be a period or an asterisk or a lowercase letter. Goals or another array, it is also equal to r times c, and it has stored in it 0 if it is not a goal cell, and 1 if the cell is a goal cell. So that's how you can determine if a cell is a goal cell or not. You also have a colors vector, which has 256 elements, which corresponds to the different ASCII characters you can put in it. Then to get a value for an ASCII character, you can call it with colors indexed at the ASCII character. In this case, it's P, which gives you a value of 2. So the color purple, in this case, scores 2 points. SPRead also does a bunch of error checking for you, and it is a good program to build your other programs on. So as you're writing your other programs, you can copy SPRead as a base program and just make your changes on top of it to build up the new functionality. So the first program you're going to write is SPAnalyze, and you should start with SPRead as a base and then change it so that it prints out all possible scoring sets. So in the example before, which is input 1, there are 2 scoring sets, a 10 purple cell in the upper right corner and a set of 6 green cells. So when you run your SPAnalyze program on it, it should print out those 2 scoring sets. So it will give you the size, the character that can be scored, and one of the cells in the goal that you could use to collect that color. For your printout, it doesn't matter which order you print out the scoring cells, and it also doesn't matter which scoring cell you print out as long as it is a valid goal cell that has that group in it. So both of these outputs are valid for this program. And then for this, think about how you'd use disjoint sets to implement it. It's a pretty straightforward connected component application. So you should augment your Superball class with a disjoint set and use a method called analyze Superball, which will perform the analysis and print out how many scoring sets you have. So here's another example file, an input file. And this example has 4 scoring sets, so it prints out each of the scoring sets. When I did program 2, I added my disjoint set to the Superball class, and I created a method called analyze Superball. I updated the constructor so that it would calculate my disjoint sets for each of the cells. And then in my analyze Superball class, I would just go through all of the goal cells, checking each one once in the group, and then counting how many connected cells there are. If there is more than the minimum size, then I would print out that grouping. The second program you're going to write is the player program. This is what's going to actually play the game to try to get as high a score as possible. It'll take the same arguments and inputs as SPAnalyze. However, now it'll print out one valid move, either a swap move or a score move with legal values. If you have fewer than 5 pieces and cannot score, you lose the game, and your output should just swap 2 random colors at the end so that the game can finish. So you get your SP player can't hang at any point. It's got to make a move even if there's no good moves available. The SP player program takes as its 5th argument the name of the program to use for input. So he has 3 example game players in the directory: SP Play, SP Play 2, and SP Play 3. SP Play works by randomly choosing 2 cells to swap, so it's a really naive algorithm, and it scores when it's possible to make a score. The other 2 are smarter, but they're not the best that you can do. So and then SP Player creates a temporary file, so you need to run it from your own directory. So you can't run it from Dr. Plunk's directory. And then, so here's an example. If you run it with yes and yes, you'll do it in interactive mode. So it'll actually step through, and you can see what it's doing at each step. So initially, it prints out the base board, and it waits for you to hit enter. Once it hit enters, it runs your program, prints out what move your program said to use, and then prints out the new board after that move was made. And you can keep hitting enter and step through each board as your program plays the game. If you say no for the 6th argument, then your program will run and it'll print out all the output, but it won't wait for you to move on to the next step. So in this case, it prints out the base, prints out a bunch of steps in the middle, and then prints out the end condition with the final score. The seventh argument can also be a no, and in that case, it will only print out the final score when it runs. So in this case, you have an in for the seventh argument, and the program prints out game over with the final score that it got from playing the game. It's possible for your program to take a long time to run. If it appears to be hanging, either because you have an infinite loop or it can't make a decision, you can send it the quit signal, and then it'll print out what the current score is. So that way, if it gets stuck, you can see what score it got to before it got stuck. There's also a shell script called run multiple, which will run the player on multiple seeds and average the results together. So, for instance, you do, in this example, you're running run multiple on the game. You're giving it SP play, and you're running it for 10 game iterations with the starting seed of 1. So it runs the game 10 times, gives you the score for each run, and then gives you the average of all the runs. And as you can see, the SP Play 2 and SP Play 3 do much better than SP Play 1 at solving the problem. In order to get meaningful runs or meaningful average, you'll have to run it more than 10 times, but you can choose how long you want to run it for. And make sure your program runs in a reasonable time. So a guideline is roughly 5 seconds for every 1,000 points it scores. If you're taking longer than that, make sure your final score is much greater than Dr. Planck's examples. And so when we're grading it, we'll be expecting this kind of performance on it. So as we're doing our grade script, or doing our grading process, we'll expect around 5 seconds for each 1,000 points you score, just to have an upper bound on how long you can take to to make a next move. For this lab, there's also a challenge associated with it. To get credit for the lab, the bare minimum you have to do is to average over 100 points on 100 games. So what we'll do is we'll use this run script on a seed that we'll choose, and half of the grade script, like lab grade, will be what the average came out to be. So you're aiming for over 100 average for 100 runs. There's also a tournament that you'll be entered into, and with all the people in the class. And if you're in first place with the highest score, you'll have 40 extra lab points added on. Second place will get you 25 extra lab points, and third place will give you 10 extra lab points. So this challenge has been performed 7 times in the past, and there's now a Hall of Fame for the best Superball scores. And to get on the Hall of Fame, you have to get an average score of over 500. And so you can see the scores from the past. Each year it gets more and more competitive. So the top 2 places are held by a team of people from 2015 when they took the class. So this is kind of like the goals you should shoot for if you want to be the best at Superball. And then some hints. You can try whatever strategy you want. And a good way of figuring out what a good strategy would be is to just play the game yourself. So just keep playing the game over and over and figure out what strategy you're using when you play the game, and then try to figure out a way to code up that strategy so that the game player can play it well also. One good way of making the game player is to come up with a rating for the board. So each board has a rating on how good it is. So when you're deciding if you should make a switch, you can enumerate all the switches and then rate the board. And if that switch leaves the board in a better state than than it was in before the switch, that would be a good move to make. So you can just basically make the switch for a swap that results in the best board rating at the end. And then so basically you can just analyze each move you can make and choose the one that you think is the best. So when I was doing it, I wrote multiple programs to help me analyze each part. So I had a find connected cells, which would do the disjoint set and find all the connections. I did an analyze collect, which would analyze any collection options I had and choose which one was the best. I had a analyze swap, which would do an enumeration of all the swaps I care about and analyze the resulting boards. So then I also had like a rate board function, which would determine how good the new board I thought it was. And then I'd have a make move function, which would just figure out what move I wanted to make and print out that move. So the other advice is when you're setting up the includes, you should have the pound include dj.h, which is the disjoint set header file. We're expecting that in your code, so when you submit your code files, you're only going to submit those 2 CPP files, but we're going to compile it with one of the disjoint set implementations, so we're expecting you to have the same dj.h included. This also means that when you go to compile your program, you'll have to do G++, the SB analyze, which is your source code for the lab step, and you'll have to choose one of the implementations of the disjoint set to compile it together. And that's about all I have. Are there any questions for this lab?